Alright, so let's go to question number 4. Question 4 reads, let f be a function from, here is a domain and here is a codomain. So the domain is all real numbers greater than 2 and the codomain is all real numbers. So the function is defined by 1 on x minus 2. Which of the following assertions are true? Alright, so we have 4 different assertions. So we need to look for the one that is true. So assertion 1 says that for every x that belongs to the domain, there exists a y that belongs to the codomain such that y is equal to f of x. That is just a definition of a function, okay? Because a function is a mapping from one set to another. So if I have a function f defined like this from a domain, maybe the interval I, to the codomain, maybe the interval j, what it means is that for every x, okay, because my function is actually y equal to f of x, okay, so my function is y equal to f of x. Now this x belongs to the domain, so for any value of x that is going to belong to the domain of the function, okay, there must exist a value of y. This value of y is the image, it belongs to the codomain. So there must exist a value of y, we call it the output. So x is what we input into the function f, and then what we get as a result is y. So y is otherwise called the image of x. These are basics of functions of Form 5. So for every x that belongs to the domain, there will exist a y that belongs to our codomain, which is j, okay, such that the y itself, which is the image, is equal to f of the point, that is f of the input, which is x. So definitely this assertion is true. All right, yes. Now so this, the definition you are going to give, you are going to say a function is defined by, you just write this down. Now the second one says, now you know that a function is either injective, surjective, or both injective and surjective, okay, or even none. Yes, no, it has to be at least one of them. And if you are injective and surjective, you are bijective, okay. Now the second one says that there exists an x that belongs to the domain such that for every y that belongs to the codomain, y is equal to f of x. That is false. That is false because of the fact that if they say that there will exist an x that will belong to the domain such that for any y that belongs to the codomain, y is equal to f of x, what they are trying to tell us, that what they are trying to say is that if you have a domain, for example, let me just say I have a particular value of x that is my domain, okay, then I have let me just say c and d in my codomain. What option B is trying to tell us is that there will exist an x that is in the domain such that for any value of y you take in the codomain, that y will be equal to f of x. So in fact, here let's try to generalize it. Let's try to check if this function is injective and if it is also surjective. Then from there we can be able to conclude, because remember that a function that is injective and surjective is a function that is bijective, and if you are a bijective function, your inverse exists. Is it okay? So if you are a bijective function, your inverse is going to exist, and your inverse is going to be unique, which means that you're going to be a one-to-one relation. So every element in the domain has one and only one mapping in the codomain. Okay, so let's verify if this function is injective and surjective. Then from there we can now use it to talk about. So for injectivity, I'll just call it in. Here, what do we need to know? We need to prove that if f of a, okay, if f of a is equal to f of b, then a is equal to b for every a and b in the domain. So if f of a equal to f of b implies that a is equal to b. Is it okay? And remember that a and b are the inputs, which means that they must belong to the domain. So a and b belong to the domain of definition of the function. If that happens, then the function is injective. Now let's verify in this case. What is f of a? It is 1 over a minus 2. Is it okay? Now what is f of b? it is 1 over b minus 2. Now if you equate, you realize that since the numerators are the same, the denominators have to be the same. So what we have is that a minus 2, so we have a minus 2 is equal to b minus 2, which just means that a is equal to b. So there's no need to write again. So if a minus 2 is equal to b minus 2, it means that a is equal to b. So this function is injective. Now, injective means 1 to 1, which means that 1 to 1 means that any element in the domain will have one will be related to another element in the codomain. Now let's verify if it is surjective. So in this case, for it to be surjective, we just need to look for the inverse, and then we show that the range of the function is equal to the codomain, and the range is a domain of the inverse. Is it okay? So we are going to let y to be equal to f of x. So y is equal to 1 over x minus 2. Then we make x the subject of the formula to be able to get the inverse. Is it okay? So from here, I can just I'll have x y. I'll cross multiply. I'll have xy minus 2y equal to 1. Then from there, I'm going to make x the subject of the formula. But first of all, I'll make xy. So what is xy? Xy is equal to 2y plus 1. Is it okay? Xy is equal to 2y plus 1. So what is now x? Our x will be equal to 2y plus 1, all divided by y. Which means that our inverse function, f inverse of x, will just be defined by, we are changing now we are going to have 2x plus 1. Remember, we changed the y to x, and there's a reason for that. All divided by x. Now what is the domain of this function? The domain is that x is not equal to 0, because it's a rational function, and for it to be defined, the denominator should not be 0. Right? So this is the domain of the inverse, which is the range of the function. But if you check the codomain of the function, you see that the codomain is a set of real numbers. The two of them are not the same, which means the function is not surjective. And if you are not surjective, automatically you are not going to be bijective, because for you to be bijective, you have to be injective and surjective. So let's go to the second proposal. Says that there exists an x in the domain, okay, such that for all any, in fact for all y that is in the codomain, y is equal to f of x. That is false, because that is not a definition of a function. Okay, our definition of a function is the first scenario, which we have marked through. Now the second one, the next one says that there exists an x in the domain such that there exists a y in the codomain that will make y to be equal to f of x. Very true. Is it okay? Because that just proves that the function is injective. Okay, injectivity means that if f of a is equal to f of b, then a is equal to b, which means where a and b are in the domain. Okay, if f of a is equal to f of b, this f of a is like y, like y1, okay, and f of b is like y2. Is it okay? So what it's saying is that if y1 is equal to y2, then a is equal to b. So this statement here is also true, because I'm not generalizing that for all. All we know is that there exists an element in the domain such that there will exist another element in the codomain that will make those two elements will exist in such a way that if you take an element from the domain and you replace it into the function, you're going to have another element in the codomain, because this is a one-to-one relation. We have clearly seen that it is injective. For example, let's take x to be equal to 1. If x 1, sorry, not 1, let's take 3. 3 is here. Okay, if you do f of 3 is going to give you 1 divided by -1. Okay, it's -1. You see that there is 3 here. Okay, is -1 in the set of real numbers? Yes. So you clearly see that because of the word there exists, then we are certain that yes, it is true. Now the last one says that for every x in the domain and for every y in the codomain, y is equal to f of x. That is false, because it's not for every x that will belong to the domain and for every y in the codomain that y will be equal to f of x. Okay, because we have seen that the function is not injective. Sorry, we have seen that the function is not surjective. Yes, the function is not surjective. So this man is false as well. But they said if we are justifying for false, we should use a counter example. Okay, that's what it says. So let's try to which counter example can we use in the last question here? So we just have to choose some values of x and y and then use it. Let's see, for every x in the domain and for every y in the codomain, y is equal to f of x. Okay, we can just use a simple counter example, right? When they say for every x in the domain, it means I can take any value of x. So if I maybe choose x, I can choose x to be equal to, I'll just choose 3. Yes. Now this one says for every y in the codomain, so I can choose y to be any value. Okay. Once they say for every, it means that no matter the value you take, it is supposed to hold. So I can take here y equal to maybe y equal to -1. Okay, so these are the two values I've chosen. Now is -1 equal to f of 3? Because and I have to check this, y equal to f of x. You see that this statement and this statement are just like this statement is true. That's why this statement is false. Why? Because the two statements are opposite to each other. If I negate the statement there exists x, I'm going to have for all x. If I negate the statement there exists y, I'm going to have for all y. So if this statement is true, then this one is false, and this is just the justification. So I've chosen x to be 3 and I've chosen y. Remember, counter example is actually proving that a statement is false. So you're taking an example to prove that that statement is false. So for every x means I can take any value of x. For every y means I can take any value of y. Then we now verify if it is true. So it's -1 equal to f of, is -1 equal, no, let me take -2 because -1 is going to work. Let me take -2. So is -2 equal to f of 3? We clearly see that it is false. Why? Because f of 3 is -1, but -2 and -1 are different. Okay, now let's come back to this other one and also justify by counter example. This one says that there exists an x that is in the domain, and for all y in the codomain, y is equal to f of x. That's also false. Yes, because we can also take x to be 3 here. Okay, and then because x equal to 3 is a specific value of x. All right, so we can take x to be 3 and take y to be even the same result, and we are not going to have an answer. But the first statement is very correct because of the fact that for every x that belongs to the domain, there will exist a y. So any x you take in the domain, there must exist a particular value that is in the codomain that will make our f of x to be equal to y. That's just a definition of a function. So for question 4, that is it that we have justified. So in the next video, we are going to move to question 5. Or in fact, let me just do question 5 in this video. Okay, question 5 says let f be a function from R to R defined by f of x equal to e to the x minus 1. This means e to the x. Okay, exponential means e to the x minus 1. So that's our f of x. So I'll just call it y equal to e to the x minus 1. Which of the following assertions are true? First one says that for every x and x prime that belongs to the set of real numbers where x is not equal to x prime, f of x will not be equal to f of x prime. Let us see if it is true. So x and x prime are in the domain, okay, and then they're telling us that x not equal to x prime implies f of x not equal to f of x prime. Yes, that is true. That is true. Okay, but let's justify. So you kind of see like this is kind of similar to the previous one on injectivity. Okay, so let's just try to verify if this function is injective. So for this function to be injective, we'll need to prove that if a is equal to b, if f of a is equal to f of b, then a is equal to b. Remember, that is the statement of injectivity. So for injectivity, if I take x, okay, and I take x prime, they belong to the domain of the function. The domain of the function is a set of real numbers. Okay, so if this happens, then so if I take any two numbers in a domain such that f of the first number is equal to f of the second number, what it means is that the two numbers are the same. So x is equal to x prime. Now this is a conditional statement, okay, and you have to note that the contrapositive of a conditional statement is the same as the statement. Okay, what we are trying to say is that in fact the contrapositive of a conditional statement, what we do is that we negate the hypothesis, we negate the conclusion, and we interchange their positions. So if I have a conditional statement, P implies Q, okay, now the contrapositive is the statement not Q implies not P, but the two of them are the same. That's what you have to note. The two of them are logically equivalent to each other. Is it okay? So the statement P implies Q and the statement not Q implies not P are the same. This statement here is called the contrapositive of this statement. Okay, so this is the definition of a function being injective. Now we can also twist the definition using the contrapositive, because if I negate this and interchange their positions, what I'm going to have is that I'm going to have the equivalence. If I negate this, what do I have? X is not equal to x prime. That's the negation of Q, which will also imply the negation of P, which will imply that our f of x is not also equal to f of x prime. So this is another definition of an injective function. This is another definition of an injective function. Is it okay? So for the first statement to be true, we will need that the function is supposed to be injective. Because if the function is injective, we either use the first definition or its equivalence, which is the second definition. So let us verify if this function is injective. So for this function to be injective, we just need that e to the x minus minus 1 should be equal to e to the x prime minus 1. And we now verify if x is equal to x prime. Is it okay? So you are going to put this down into writing. Okay, so for you to be injective, we have e to the x minus 1 must be, if e to the x minus 1 is equal to e to the x prime minus 1, what it means is that x is equal to x prime. But let us see what this actually means. So negative 1 cancels on both sides, and we just have e to the x, okay, e to the x equal to e to the x prime. Now in indices, when the bases are the same, we just equate their powers. So from here we are very certain that x will be equal to x prime. So we clearly see that f of x equal to f of x prime implies x is equal to x prime. But this is also the equivalence, which makes the function to be injective. So the first assertion is true. Now let's go to the second assertion. For every x and x prime that belongs to the domain, x not equal to x prime is implied by f of x not equal to f of x prime. So instead, what it means is we are actually starting by with the first statement. Okay, we are starting by with the first statement. All right, and the first statement is saying that so if you want to read it normally, what we are going to say is that f of x not equal to f of x prime implies that x is not equal to x prime, which is actually true. Okay, which is actually true, because if I just put not equal to here, I'm going to have not equal to, and I'm going to have not equal to, which is making everything to also be true. So I think that for injectivity, I think it is, the statement is actually if and only if. Yes, it's supposed to be if and only if. Yes. Now let's go to the third one. So this third one says that for every x and x prime in the domain of the function, x not equal to x prime implies that for every y that is in arrow, f of x is less than y less than f of x prime. This is actually testing the kind of the injectivity of the function, sorry, the monotony of the function. Is it okay? So here we need to verify if the function is increasing or decreasing. Is it okay? So I think I'll have to take you guys to Microsoft Word there. So we have that our function f of x is equal to e to the x minus 1. Is it okay? So let us check if this function is increasing or it is not increasing. So let's do f prime of x. What do we have? We have e to the x, but we know that e to the x is always positive for any value of x, because the exponential function is a positive function. Is it okay? So what we are saying is that the function f of x is increasing, because when f prime is positive, f is increasing. Is it okay? And if f is increasing, now this is the definition. So f is, so let me give you another definition of an increasing function. F is increasing. In the layman terms, what we mean is that as the values of x are increasing, the function itself is increasing. What it means is that whenever x1, for example, or let me say whenever x is less than x prime, okay, whenever x is less than x prime, what it means is that f of x will also be less than f of x prime. Is it okay? That's another definition of an increasing function. So that if x is less than x prime, it means that x prime is bigger than x. So f of x must be also less than f of x prime, which means our f of x prime will also be bigger than f of x. When that happens, then we are very certain that this function is increasing. Is it okay? So that's the definition of an increasing function in layman terms. Going back to the equation, this proposal says that if you have two real numbers that are not equal to each other, there will exist a y in the set of real numbers that is going to make f of x to be less than y less than f of x prime. So already we have seen that our function here is an increasing function. Is it okay? Our function there is an increasing function. Okay, so definitely that proposal is correct, because if you check very well, you see that no, the proposal is not correct. Is not correct. Why is it not correct? It is going to be correct. Let us see very well. So in fact, this proposal is trying to tell us that, because if you want to look at this and this, you see that f of x will be less than f of x prime. Is it okay? Because if f of x is less than y and y is less than f of x prime, by transitivity f of x will be less than f of x prime. Just check where their inequality signs, just check where their positions are. So what this proposal is telling us is that our f of x will normally be less than our f of x prime. Okay, but it is going to depend, because x is not equal to x prime. Is it okay? So for f of x to be less than f of x prime, our x must be less than x prime. Okay, because our function is increasing. So our x being less than x prime will definitely tell us that f of x, okay, f of x will be less than f of x prime, because our function is increasing. But in the original, at the beginning of the equation, we don't know if our x is less than x prime. We just know that our x is not equal to x prime. Is it okay? So it makes the proposal to be false. Yes, it makes the proposal to be false. So you have to put this down into writing. Now the last one says that for every x and x prime in the set of real numbers, f of x times f of x prime less than 0 means that x times x prime is less than 0. No, that is false. That should be false. That should be false. That should be false. And I think we can do a counter example here. Yeah, we can do a counter example. Because if f of x is less than, if f of x times f of x prime is less than 0, it does not mean that x times x prime is also less than 0. Yes, it does not mean that. Because let me take for example. So for this last part, let me just take x to be equal to take x to be equal to 0. Okay, yes, in fact, just taking x to be equal to 0 already spoils everything. Yes, so this man is false, because if you take x to be equal to 0 and Okay, no. X equal to 0 will not make it to be less than 0, so we cannot take x to be equal to 0. Let me change it. So let me take x to be equal to -1. Okay, if I take x to be equal to -1, okay, maybe take x to be equal to -1 and take x prime to be equal to 1. If we do f of x, our f of x will give us e to the power -1 minus 1. The result is negative clearly if you punch on your calculator. If you do f of 1, it will be e to the power 1 minus 1, which is positive. Is it okay? It's positive. No, this counter example does not really work, because if you multiply -1 and 1, the result is clearly less than 0. The result is clearly less than 0. In fact, can this proposal be true? Can this really be true? Let's try to see again. If I multiply f of x and f of x prime and the result is negative, does it mean that the x and the x prime is, the product of x and x prime is negative? In fact, let us try to solve this part. Okay, f of x times f of x prime being negative, what it means is that our f of x and f of x prime will have opposite signs, because it is only when you multiply two quantities with different signs that the result will be less than 0. Is it okay? So we can have f of x being negative. Okay, we can have f of x being negative and then f of x prime being positive, or vice versa, or we can have f of x being positive and then f of x prime being negative. Is it okay? So let's analyze those two situations. Okay, let's analyze those two situations. So let's take case 1. Okay, let's take case 1 when f of x is positive and f of x prime is negative. Now what it means is that e to the x minus 1 is positive and e to the power x prime minus 1 is negative. So the first solution will be e to the x is bigger than 1, and the second solution will be e to the x prime is less than 1. So we are going to have, if e to the x is bigger than 1, okay, this one is actually the same as e to the power 0, okay, and this other one is also the same as e to the power 0. So since all the bases are bigger than 1, I'm just going to get, for the first case, x greater than 0. I'm going to have x greater than 0, and for the second case, x prime will be less than 0. So these are my two, so you see, in the first case, in our first situation, when f of x is greater than 0 and f of x prime is less than 0, we have that our x is greater than 0 and our x prime is less than 0. And if you see, if you multiply x and x prime, the result will be less than 0, which is going to actually tie with our explanation here. But let's take the second case before we conclude. Is it okay? So for case 2, because normally if I take something that is positive and multiply with something that is negative, the result will be negative. Let me take case 2. So for case 2, we are going to now take, instead, f of x will be less than 0 and f of x prime will be greater than 0. In fact, if we solve, we are just going to have our x will be less than 0 and our x prime will be greater than 0. And if you multiply the two quantities, the result will still be less than 0. So yes, this option is true. Yes, this option is true. Okay, so we are done with question 5. So in the next video, I'm going to do question 6. I think this video is already long since we did 2 questions here.